Welcome back to Fundamentals of AC Circuits. In this video, we are going to discuss capacitors and inductors. So the learning objectives for this video are that you will be able to describe the basic construction and characteristics of capacitors and inductors. We're going to discuss the various types of capacitors and inductors, and then we'll analyze how we handle a circuit with capacitors and inductors that are placed in series or in parallel, as well as how these two elements respond to an AC source. So first, let's talk about what a capacitor is. It's considered one of the fundamental passive components. In its most basic form, a capacitor has two plates that are separated by what's called a dielectric, which is an insulating material. Remember that an insulating material does not allow the flow of current. So you have two plates on either side of the capacitor. Those are your conductors. Those are made of a material that will conduct electricity. And in the middle of these two plates, they're separated by that dielectric. The ability to store charge is the definition of capacitance. And capacitors are elements that can store electric charge. So first, let's talk about the charging process for a capacitor. So on the screen, you can see a diagram where you have the two plates and the dielectric that separates them in the middle. The leads on either end are like your wires that stick out on either end, and that's where you would connect your capacitor to a circuit. So if we were to zoom in on the material of the two plates, the material would be made up of protons and electrons at the atomic level. And what's going to happen is there's going to be a movement of electrons that will cause the plates to become polarized, and that will then hold a charge. So initially, a capacitor is uncharged. So before you place it into a circuit, we're going to assume we're starting from the point of it's initially uncharged. Once you connect that capacitor to a voltage source, like the one shown in the picture, we now have a complete circuit where electrons can flow from one plate to another. Notice that on the plate on the left, there are electrons that are going to flow from plate A around the circuit to plate B. Keep in mind this dielectric prohibits the flow of electrons, so there's only one path for current to take, and that's right around like this. So these electrons are going to move from plate A around the circuit and onto plate B. Once the capacitor is fully charged, what we'll have are plates that have become polarized because the electrons and the protons are now unbalanced. Many of the electrons have left this plate, plate A, traveled around the circuit, and traveled to plate B. So now we have an excess of electrons on one side of the plate. And we consider the capacitor to be fully charged when this plate can no longer hold any additional electrons. And at that point, there will be there will cease to be a flow of electrons around the circuit once it is fully charged. So once the capacitor is charged, we can remove the voltage source. We can take that completely away. And at this point, your capacitor is like a temporary battery. It has a certain amount of electric charge that has been stored, and you can take this capacitor, place it into a circuit, and it will act as a temporary voltage source or a temporary battery for a certain amount of time. The capacitance is the ratio of charge to voltage. Notice that charge is represented with a Q, capacitance is represented with a C, and voltage is represented with a V. So we can rearrange that equation if we need to determine the amount of charge on a capacitor, and the amount of charge that a capacitor can store is determined by the size of the capacitor, its capacitance, and the voltage applied. So here are some different types of capacitors that you will see in a lab environment. There are mica capacitors. They're very small, they're flat, and they are orange. And they are literally pieces of foil and a material called mica that are layered together. Mica capacitors are very small in size, but they have a high working voltage. Keep in mind with capacitors, they are all rated to be connected to a certain maximum level of voltage. And so you will have to review the ratings for the capacitors that you're using whenever you are generating a circuit that uses capacitors. Mica capacitors are known for being small with a high working voltage. That means you can connect them to a high source voltage. There are ceramic disc capacitors, which are also flat, small. These ones are rounded as opposed to more of the square shape for a mica capacitor. They are small, they are non-polarized. Polarized basically means that the two silver prongs on either end are like a positive and negative terminal of a battery. So if you don't put the capacitor in the right way, you can damage your circuit. So if a capacitor is polarized, you have to take note of that. These ones are non-polarized. They're plastic film capacitors. These ones have a small round cylinder body. They're typically silver with your two leads on either end. These are also non-polarized. They have a relatively high capacitance due to the larger surface area on the plate. And then you have electrolytic capacitors. These are ones that are polarized. If you took the Intro to Engineering Technology course at Valencia College and you did the soldering project, you should have soldered onto your board a few electrolytic capacitors, and one lead is longer than the other. So you have to pay attention to that. The longer lead is the positive terminal, so if you are to use a polarized capacitor, you have to know which terminal is positive and negative. If you put it in backwards, the capacitor has the potential to explode once you turn power on to that circuit. So you do have to keep aware of the types of capacitors you're using and whether they are polarized or non-polarized. So when capacitors are connected in series, the total capacitance is smaller than the smallest one. So in general, the equation for capacitors in series is shown on the screen. Now this is the exact same formula that you would use for resistors that are in parallel. So capacitors and resistors sort of have an opposite relationship when it comes to how they're wired. Capacitors in series can be combined so that you get a total equivalent capacitance, but you will combine them by using the same formula that you use for resistors in parallel. So if you have two capacitors in series, you can shorten the equation up above to just show for two capacitors. You can also use what's called the product over sum rule. So if you have two capacitors in series and you want to combine them, these two formulas are equivalent. That's the product over sum rule. So those two formulas are equivalent. You can use either one of those to combine two capacitors that are in series. When you have capacitors that are in series, they can act as a voltage divider. And here's our general equation for a voltage divider. Notice V sub X is the voltage across a particular capacitor, capacitor X. And what we're going to do to set up that voltage divider is take the total capacitance of all your capacitors that are in series, divide by the capacitance of the specific capacitor you want the voltage drop for, and then multiply by the total voltage across all of your capacitors in series. So in general, capacitors in series work as a voltage divider in the same way that you think of resistors in a voltage divider. The equation to set it up is slightly different. Notice that the total is on the top and not the bottom. But other than that, we can take a group of capacitors that are wired in series and apply a voltage divider to find the voltage drop across a specific capacitor. So here's a quick example that's using the voltage divider. We're going to calculate the equivalent capacitance for this circuit below and then find the voltage across each capacitor. So these are all in series, so we can combine them. We're going to treat them the same way we would treat resistors that are in parallel. Also be aware of all the units. So that's microfarads is the unit you see on the screen. The unit of measurement for a capacitor is the farad, named after a man named Farad, who did a lot of work in developing and studying capacitors. So our unit for capacitance is the farad, and then these particular capacitors are in microfarads. So be sure that when you type these calculations into your calculator that you're not doing 1 divided by 0.1, you're doing 1 divided by 0.1 times 10 to the negative 6, and so on. So we can combine these three capacitors using the equation shown a few slides ago, and you'll get that the equivalent capacitance is 60 nanofarads. Next, we can set up a voltage divider using the voltage divider equation for capacitors in series. So we're going to take the total capacitance. We're going to divide that by the capacitance of the particular capacitor we want the voltage drop for, and then multiply by the source voltage. So we can get the voltage drop across the first capacitor by plugging in CT on the top the capacitance for C1 on the bottom, and multiplying by the source, which is 25 volts. We can repeat this process for the other two capacitors by changing the denominator in the fraction of the voltage divider equation. When we have capacitors in parallel, the total capacitance is the sum of each individual capacitor, and the general equation for capacitors in parallel is just to add them all up. So capacitors in parallel can be thought of the same way we think of resistors in series. We can combine them to get an equivalent capacitance by adding each individual value together. So, as a quick example, if you have two capacitors, C1 and C2, as shown on the screen, to combine those in parallel, we're simply going to add those together, which gives you 1800 picofarads. So we're going to do another example using two capacitors in parallel. We're going to calculate the total equivalent capacitance, and we're going to find the voltage across each capacitor. To start with, find the total capacitance by simply adding these two capacitors together. They're in parallel, so we're going to combine them. And you're going to get 550 picofarads. And just as a reminder, the same way that we would consider the voltage drop across parallel resistors to be equal to each other and equal to the source as long as they are in parallel with the source, the same is true for capacitors. These two capacitors are in parallel with each other and they're in parallel with the source. Therefore, the voltage drop across them must be 5 volts. So, we're going to talk a little bit more about the charging process with a capacitor. A capacitor will charge when it is connected to a DC voltage source as shown here. So earlier I gave a quick introduction of what's happening when you connect a capacitor to a source. Initially it's uncharged. See how the switch is open here? So this is an uncharged capacitor. When the switch is closed and a complete circuit is formed, electrons will travel from plate A to plate B. Plate B will become polarized because it'll have more electrons than plate A. So we can consider plate A to be positive and plate B to be negative in terms of polarity. At some point, plate B will no longer be able to accept any more electrons. And at that point, we say that the capacitor is fully charged. Once plate B can no longer accept any more electrons, there will be no flow of current through the circuit. Therefore, current will be 0. Once you open the switch, there will not be a flow of current in this circuit, but your capacitor remains charged. It has a level of electrons that can be used to generate current if this capacitor were placed into another circuit. So this is the charging process when a capacitor is connected to a DC source. A few things to remember: when the capacitor is fully charged, there is no current, and a capacitor blocks constant DC, meaning once the capacitor is fully charged, this DC source is basically doing nothing. It's blocked by the capacitor. No current is flowing in the circuit. When a capacitor is charged through a series resistor and a DC source, there is an exponential charging curve that you can observe. So let's say that this is our circuit, and here there's a switch here. The exact millisecond that the switch is closed, your capacitor is going to begin to charge until it gets to some final amount. And the curve that shows how the capacitor will charge is over here on the right. As time goes on, the amount of voltage will rise and rise and rise until it hits a final point where it can charge no further. And so we have an exponential curve that shows how a capacitor will charge. You can also see how the current will flow as a function of time when the capacitor begins to charge. So when the switch is closed, we have our maximum amount of current, and the current will exponentially decrease until the capacitor is fully charged. Once the capacitor is fully charged, no more electrons are going to flow in that circuit because remember how plate B can no longer accept any more electrons, and at that point there is no more current when we get to the point that the capacitor is fully charged. So, something to keep in mind, a charged capacitor can remain charged for long periods of time, depending on something called its leakage resistance. Therefore, a charged capacitor can cause electric shock. So, if you were working in a laboratory environment and you happen to walk past a bench or a desk where a capacitor is just sitting there, if you don't know how someone else has used that particular component, you have to be careful and assume that it could be charged. And if you were to pick up that capacitor and touch the leads with your fingers, you could potentially be shocked, even severely shocked, depending on the size of the capacitor and how much charge it can store. All right, so when we have our charged capacitor, it has retained its charge from being connected to a DC source, and we're going to then connect a wire across the two leads of the capacitor. Then the capacitor will begin to discharge. So all of the extra electrons that have been stored on plate B will begin to travel back around to plate A until these two plates reach an equilibrium where the amount of charge on each plate is equal. And at that point, the capacitor is now uncharged. All of the charge that it had stored has now been distributed back across the circuit to plate A. So this is how a capacitor works. It stores charge when you connect it to a DC source, and then you can take that capacitor and use it as a temporary voltage source, keeping in mind that as soon as you allow the capacitor to discharge, it is going to begin losing charge over time until it gets to a point where it is completely uncharged. Also remember that there is no current running through the dielectric, that insulating material between the two plates. There's no current that flows through that dielectric when you're charging or discharging. It's an insulating material. Electrons will simply flow from one plate to another. So when a capacitor is discharged through a resistor, the discharge curve is also exponential. So let's say that we have a charged capacitor, and we're going to connect that capacitor to a resistor. And here's our switch. So when we close the switch, this charged capacitor will effectively become our voltage source for a temporary amount of time. And the charge that has been stored from the capacitor is what's going to cause the flow of current. So an initially charged capacitor will have a certain voltage level, and as time continues, it will discharge. And this curve shows that exponential discharge. The same thing with discharging current. Once that switch is closed, we'll have a value of current that's flowing through the circuit, and that'll be the maximum amount of current that you'll have as your initial current. And as that capacitor discharges, the amount of current flowing through the circuit will also decrease exponentially until there is no more voltage or no more charge stored within the capacitor, and therefore there's no more current flowing through the circuit. So in a practical situation, there cannot be capacitance without some resistance. So this introduces the idea of time, that there is an element of time in the charging and discharging of a capacitor. And the way that we can study that element of time is to look at the time constant. So when we have a series RC circuit, that means a resistor and a capacitor in series, we can have what's called the time constant for that circuit, and that time constant is what determines the rate at which the capacitor charges or discharges. How quickly or how slowly will that capacitor charge? Your time constant is what's going to determine that. We call the time constant tau. This is the Greek letter tau, and it's simply your level of resistance multiplied by your level of capacitance in the circuit. The time constant is a time value, so your unit for the time constant will be in seconds. So when a capacitor is charging or discharging between two voltage levels, the charge in the capacitor changes by approximately 63% of the difference in levels in one time constant. So in other words, an uncharged capacitor can charge to 63% of its maximum value in one time constant. So if your time constant was 5 milliseconds, you can go from 0 volts to 63% of the maximum voltage you're ever going to have for that capacitor in that amount of time. And for discharging, it works the same way. If you have a fully charged capacitor, you're going to lose 63% of your voltage in one time constant. So whether we're charging or discharging, we have these relationships that are going to stay true. And you can see these relationships in the charging curves on the right. So for a capacitor that is charging, after one time constant, remember you're going to take R and C, multiply them together, that's going to give you an amount of time. After one time constant, you're going to go from 0% voltage to 63% of your maximum voltage just in that amount of time. In 2 time constants, you'll get to 86%. In 3 time constants, you'll get to 95%. And 4 constants, you'll get to 98%. And by the 5th time constant, you're basically fully charged. So that's how your charging curve will look for any RC circuit. For any capacitor that's in series with a resistor, that capacitor is going to charge at a certain rate. This curve determines the rate. These percentages will never change. The only thing that will change is what the actual value of your time constant is based on the resistance and the capacitance in your circuit. Discharging is the same way. If you start with a fully charged capacitor, you'll go from a 100% charge to 37% charge in 1 time constant. By the 2nd time constant, you're at 14%. By the 3rd constant, you're at 5%. By the 4th constant, you're at 2%. And by the 5th time constant, you're basically at 0%. You're fully discharged once you pass the 5th time constant. So these are our charging and discharging curves that show the process of how a capacitor will charge and discharge with time. So these curves have a formula. We call this the general voltage formula for RC circuits. And this formula here is based on a couple of values. We have V sub F, which is the final value of voltage. What's the maximum level of voltage this capacitor can be charged to? VI is your initial value of voltage. How much voltage am I starting out with? And V, this lowercase v, is your instantaneous value of voltage. Notice that within this equation, we're saying that the instantaneous value, so the voltage at a specific moment in time, is equal to your final voltage plus your initial voltage minus your final voltage as a quantity times E. Now this is the constant E. So that's E raised to the power of negative T. That's how much time has passed. So T is time divided by RC. That's your time constant. So again, this is the constant number E. Just like pi, we have that's a constant. That's what this E is here. It's the constant E. And this formula here basically tells you the instantaneous value of voltage for any point in time. So if I plug in the final value, the initial value, the amount of time that has passed, and the RC time constant, I can know exactly how much voltage that capacitor will have charged to in that amount of time. So let's put this equation into practice. Using the figure shown, we're going to determine the capacitor voltage 50 microseconds after the switch is closed if the capacitor is initially uncharged, and then we're going to draw the charging curve. So we're going to start by calculating the time constant, which is R times C. So we have 8.2 kiloohms times 0.01 microfarads, which gives you 82 microseconds. We need that time constant in order to draw the charging curve and to figure out how much charge how much charge the capacitor will have 50 microseconds after the switch has closed. Next, we're going to use our voltage equation and plug in what we know. So here are some things that we know. We know that the capacitor is initially uncharged, so the initial value has to be 0. The final value for the capacitor is related to the source. The capacitor can be charged only as great as the source that's being applied. So if the switch were closed long enough and the capacitor was able to fully charge, the largest level or the final value of voltage that this capacitor will charge to is 50 volts based on the source. So we know that VF is 50. We know the amount of time that is passing, where we want to know the voltage after 50 microseconds. So time, this T right here, is 50. And then tau is our time constant, which we know to be 82 microseconds. So we're going to plug all of these values into the equation and solve it. Once you type all of this into your calculator, you will get that the instantaneous value of the voltage at exactly 50 microseconds is 22.8 volts. So we know that's how much voltage the capacitor has stored after 50 microseconds. And now we're going to draw the charging curve. In order to do that, you need to know the value of the voltage for the first 5 time constants. So we are going to, let me go back. We're going to rely on these percentages here. These percentages will never change. So after 1 time constant, you're going to have 63% of your final value. After 2 time constants, you'll have 86. After 3, 95. After 4, 98. And after 5 time constants, you have 99%. We can use these time constants to figure out the charging curve for this particular circuit. So after 1 time constant, meaning after 82 microseconds, your voltage is going to be 63% of your maximum value or your final value. After 2 time constants, it'll be 86% of your final value. After 3 time constants, you'll have 95%. After 4 time constants, you'll have 98%. After 5 time constants, you'll have 99% of your final value. So when I plot this as a graph, on my x-axis, I'm going to be plotting my time constants. On the y-axis, I'll plot voltage. Here's what your graph will look like. This is my curve showing at 0 microseconds, we have 0 voltage. And it's going to take approximately 410 microseconds for it to fully charge to the maximum value of 50 volts. After that, this curve will stay flat. It will not go any higher than 50. And at that point, the capacitor will just stay charged until it's given an opportunity to discharge. So here's another example. The question is, how long will it take the capacitor below to discharge to 25 volts when the switch is closed? Now, before we start calculating anything, take a close look at what this circuit is. It's a capacitor. There's no voltage source, but the capacitor is labeled. It's labeled as 100 volts. So I can take that to mean that this capacitor has been charged to 100 volts, and this is going to be a temporary source of voltage once that switch is closed. Over time, this capacitor will discharge, and eventually it'll have no current to provide. But right now, we know it has a voltage across it of 100 volts, and it can generate a current that will flow through R. That's what we know. So the question is, how long will it take the capacitor to discharge to 25 volts? If I'm starting at 100 volts, how long will it take before there are only 25 volts left across that capacitor? So first, let's start by calculating the time constant. We know the time constant is R times C. So that'll give you 2.2 milliseconds as your time constant. Next, we're going to look back at our general voltage formula and fill in the things that we know. Let's start with our initial and final values. This capacitor is a charged capacitor. It's charged to 100 volts. That's your initial value. Your final value will be what the capacitor will discharge to. So it'll discharge to 0 volts. We're starting at 100. Eventually, it will discharge to 0. So those are your initial and final values. So keep in mind those initial and final values are going to change based on whether you're charging or discharging. When you're charging, your initial value is 0. When you're discharging, your initial value will be what the capacitor has already been charged to. The other thing we know is our instantaneous voltage. The question is, how long will it take to discharge to 25 volts? That's an instantaneous voltage. That's a voltage at a certain point in time throughout the discharging process. So that's actually going to be our V on the left-hand side of the equation. And what we don't know is T. We don't know time. So we're going to plug in our initial and our final values, our instantaneous value, the time constant, and solve that for T. So here's what we have. Now we're going to simplify. Divide both sides by 100. And if you don't remember anything about natural logarithms, that is what we're going to use to get rid of the E in this equation. So the natural logarithm is what's going to cancel out the E. You just have to make sure you take the natural logarithm of both sides of the equation. So the natural logarithm on both sides, on the right side, this natural logarithm will cancel out the E, and you'll be left with just the fraction as a fraction. Then you can multiply both sides by the 2.2 milliseconds. Remember, that's 2.2 times 10 to the negative 3. And it's going to take 3.058 milliseconds for this capacitor to discharge from 100 volts to 25 volts once the switch is closed. That's how we attack a problem like that. Next, we're going to move on to something really important called capacitive reactance. Capacitive reactance is the opposition to an AC signal by a capacitor expressed in ohms. Earlier, you learned that resistors provide an opposition to the flow of current, and we call that value resistance. Well, capacitors also provide an opposition to an AC signal, and we call that capacitive reactance. The equation for capacitive reactance is 1 divided by 2 pi fc. You know what pi stands for, 3.14. F is going to be the frequency of your AC signal. So you're going to have a circuit that's going to have an AC source. Remember, that's going to be a circuit that's delivering a sine wave. And that sine wave has a particular frequency. You're going to use that frequency for F. C is the value of capacitance for your capacitor. And X is what we're going to use to refer to the term capacitive reactance, X sub C. So for the duration of this course, anytime you see X sub C, that is the variable or the letter name that we will use for capacitive reactance. So if we're going to calculate the capacitive reactance of a 0.047 millifarad capacitor when a frequency of 15 kilohertz is applied, we're going to plug 15 kilohertz in right there. We're going to plug the 0.047 millifarads in right there for C. We're going to do 1 divided by 2 pi fc, and you'll get 226. Now the unit for capacitive reactance is ohms. We're going to treat that like an impedance, like we would treat a resistance value. So when you calculate capacitive reactance, one thing you're doing is putting a capacitor on the same playing field as a resistor. Now that the unit is ohms, we could take a resistor and a capacitor and combine them so that we can figure out a total impedance or the total opposition to an AC signal in a circuit when we have different elements within the circuit. So when capacitors are in series, the total capacitive reactance is going to be the sum of each individual capacitive reactance. So earlier we discussed that when capacitors are in series, we can combine each capacitor by treating them the same way we would treat parallel resistors. Or we can take each capacitor's value for capacitive reactance, and then we can add them together just like we would add series resistors. Capacitors in parallel can be combined by taking each capacitive reactance and then treating them the same way we treat parallel resistors. So it's going to be a little bit difficult to keep straight at first. Just make sure that you study and practice. When we're looking at capacitors just by themselves, like maybe capacitors in a DC circuit. In a DC circuit, there is no capacitive reactance. So when we're looking at capacitors by themselves, we can combine them when they're in series or when they're in parallel. But that's going to be the inverse relationship to how we combine resistors. But if we take every capacitor and transform it into a capacitive reactance when we have an AC circuit with an AC source, now all of those capacitive reactances can be treated the same way we treat resistors. Once we have capacitive reactance, we can start to apply Ohm's law to our circuits. So we can solve for the current in a circuit, for example, by taking the voltage source divided by the capacitive reactance. Just remember that when you apply Ohm's law in an AC circuit, everything must be expressed the same way when you express voltage and current. Peak to peak, RMS, peak, etc. So here's an example. A sinusoidal voltage is applied to a 0.0047 microfarad capacitor. The frequency of the sine wave is 1 kilohertz. Determine the capacitive reactance. You just need to remember the formula, 1 divided by 2 pi fc. That formula you will use 200 or 300 times this semester at least. You need to memorize it. Just by doing the homework alone, you will memorize it. It will not be given to you on a reference sheet for an exam. So 1 divided by 2 pi fc, that is your formula for capacitive reactance. You're going to plug in your values for F and C, remembering engineering notation. So this is 1 kilohertz. Make sure you type that in as 1 times 10 to the third, or 1,000, or 1E3. Make sure you're doing that in some way, shape, or form when you're typing this in your calculator. Make sure you're also typing in these units correctly. 0.0047 times 10 to the negative 6. That's this unit here. So as long as you're typing in everything correctly, you should get what I have on the screen, 33.86 kiloohms. So here are two circuits, and we're going to find the total capacitive reactance of each circuit. We're going to start with the circuit on the left. And in order to do anything with either one of these circuits, the first thing we're going to do is calculate the capacitive reactance of each capacitor. So for capacitor 1, we're going to do 1 divided by 2 pi fc. First, find the frequency. It'll always be labeled by your source or given to you in the directions. The frequency is rarely, if not ever, something you will calculate. That's a given or a known quantity. So you're going to plug in the frequency, and then you're going to plug in the capacitance for C1 to get the capacitive reactance for C1. And we call that XC1. You get 3.18 kiloohms. Repeat this process for C2, replacing the value on the bottom for C2, and you get 468 ohms. Now that you've transformed these capacitor values into a capacitive reactance value, you can treat these values like resistors. These are in series, so you can add these together to get the total capacitive reactance for this circuit. These are in parallel, so you can treat them like parallel resistors to get the total capacitive reactance for the circuit. Now, that's not the only way you could have done this problem. You could have combined these capacitors first into a total equivalent capacitance, and then found the total capacitive reactance for that total. You'll get the same number. So you could have done it that way too. Either way you choose is fine. Next, we're going to determine the RMS current in the circuit below. Notice you have an RMS voltage given, a frequency of 10 kilohertz, and you have a capacitor. We're going to start by finding the capacitive reactance, which is 1 over 2 pi fc. Plug in your frequency and your capacitance level, and you'll get 2.84 kiloohms. And then we can apply Ohm's law. We can take the RMS voltage given, divide by the capacitive reactance we calculated, and we have an RMS current as our output, 1.76 milliamps. You can also set up a capacitive voltage divider using capacitive reactance instead of actual capacitor values. If you do that, it's going to work the same way that a resistive voltage divider works. You're just going to replace the resistance values you would normally have in your voltage divider with capacitive reactance values. And then you can set up a voltage divider the same way that you have done in DC circuits. So we're going to quickly practice that. Notice we have two capacitors that are in series. We have a voltage source given as 10 volts. Now, if this is not labeled any other way, that 10 volts is a peak value. So this is a sinusoidal source delivering a sine wave for your voltage. Your voltage is moving or behaving in the form of a sine wave with a peak value of 10 volts and a frequency of 5 kilohertz. So we're going to start by finding the capacitive reactance of each capacitor. 1 over 2 pi fc for each capacitor. Then we're going to set up that voltage divider the same way you would set up a voltage divider as if they were resistors, but you're going to be using these capacitive reactance values. So you need the total, and then you're going to set up your voltage divider. So the voltage across C2 is going to be XC2 divided by XCT times Vs. Plug in your values for XC2 and XCT, multiply by your source, and you have 1.28 volts as your voltage across C2. Next, we're going to quickly talk about power. Energy is stored by the capacitor during a portion of your AC cycle. So remember, your AC cycle is a sine wave. As that sine wave flows through your capacitor, during a portion of that cycle, energy is stored. During the next portion of that cycle, the same energy that was stored is returned to the source. So if you think about there was some power provided and that same amount of power provided was taken away, if you will, there's a net of 0 when it comes to true power. True power is not dissipated in a capacitor when it's in an AC circuit. Any energy that is stored is then returned to the circuit within the capacitor. And you'll also see as we start to study RC circuits next week that voltage and current are always going to be 90 degrees out of phase. So when we look at the power that is dissipated in a capacitor, there's no true power. Any energy that's stored by the capacitor is returned to the circuit for a sum total of 0. But one thing we do study with capacitors is the rate at which the capacitor stores or returns energy. So not the energy stored or returned itself, but the rate at which it's stored or returned. And we call this reactive power. The unit for reactive power is the VAR, which stands for volt ampere reactive. And with a capacitor in an AC circuit, we're going to calculate reactive power using these formulas on the screen. Your RMS voltage times your RMS current, your RMS voltage squared divided by your total capacitive reactance, or your RMS current squared multiplied by your total capacitive reactance. This is how we calculate reactive power. Reactive power. So this is the type of power that we study when we look at power in capacitors. So if you were to determine the true power and the reactive power in the circuit below, first, true power is always 0. When you have a capacitor in an AC circuit, there is no true power. It is always going to be 0. As for the reactive power, we need to know the capacitive reactance. So you're going to calculate that using the frequency and capacitance values provided. And then you can plug your RMS voltage and your capacitive reactance into the equation for power, for reactive power, and you get 503 microvars. Remember, var is the unit for reactive power. So that's it for capacitors, at least for an introduction, and now we're going to switch over and talk about inductors. So first I'm going to explain the concept behind an inductor. When a length of wire is formed into a coil, it becomes an inductor. So an inductor is a coil of wire. When current runs through the coil, a strong electromagnetic field forms within and around the coil. If you've taken Physics 2, you've studied electricity and magnetism, and you know a little bit about flux. If not, that's okay. You don't have to know about flux for this course, but the image on the right shows that magnetic field and those lines of flux that will occur when you take a coil of wire and run a current through it. As that current changes, the electromagnetic field will change. So think about a coil of wire connected to an AC source. Well, you have a voltage that's constantly changing with time, so you have a current that's also constantly changing with time. As that current changes, the electromagnetic field changes. An increase in current will expand the field, and a decrease in current will reduce the field. Changing the magnetic field of an inductor causes an induced voltage across the coil in a direction to oppose that change in current. This property is what we call inductance, and it's symbolized by the capital letter L. So this is the symbol that you'll see in multisim in the book in schematics for an inductor. Small coil of wire labeled with an L for inductance. Inductance is a measure of a coil's ability to establish an induced voltage as a result of a change in current. So when we measure inductance, we're measuring that coil's ability to establish a voltage in response to a change in current as it flows through the coil. The induced voltage is always going to oppose the change in current. If you will, you can think about how equilibrium occurs, and sometimes there is an equal and opposite reaction in order to establish an equilibrium. Sort of the same idea here. An induced voltage always opposes the change in current, which is basically a statement of Lenz's law, which is used to establish the idea of an inductor. And the unit of inductance is the Henry, which is the capital H. So here's what happens when you place an inductor in a circuit. Look at the first picture here. We have a DC source. It's 10 volts. Just before the switch closes, there's no current flowing in the circuit. No current. Once we close the switch, current begins to flow through the circuit. This ammeter is measuring current. Notice that we have a time constant, and as the time constant increases, the current increases. until we get to a maximum point. So just like a just like a capacitor will store charge over time until it gets to a final or maximum value, current will increase within an inductor in the same manner over time until it reaches a maximum or final value. Once the inductor has reached its maximum level of current, you can take a load resistor, connect that across the inductor. You can open the switch, and the current that has built up over time because of the inductor in the circuit will begin to flow through your load resistor. So the current from the inductor becomes the current that flows through your load. Your inductor becomes a current source, the same way that a capacitor can charge and then become a voltage source for another component at some other point in time. So notice that we've opened the switch. There's 10 milliamps of current flowing through the load, and over time, that number drastically drops until it goes back down to 0 after 5 time constants. So an inductor has a relationship to current, much in the same way that a capacitor has a relationship to voltage. When a DC voltage is applied to an inductor, the current flowing through the inductor increases, similar to when a capacitor begins storing charge in an RC circuit. When that DC voltage is removed, the inductor serves as a current source, and the current will begin to dissipate until the current in the inductor is 0, similar to when a capacitor discharges after a source voltage is removed. So, when inductors are connected in series, we can combine them the same way we would combine capacitors and resistors. In this case, we can treat inductors exactly the same way we would treat resistors. If they're in series, we can combine their inductance values together to get a total inductance. So if I have two inductors, L1 and L2, one is 1.5 millihenries and the other is 680 microhenries, I can add those two values together to get a total inductance of 2.18 millihenries. When inductors are connected in parallel, the total inductance is smaller than the smallest one. In other words, we combine inductors in parallel the same way we combine resistors in parallel. So we would do 1 divided by 1.5 millihenries plus 1 divided by 680 microhenries. Take that total, take the inverse of that total, you get the total inductance for these two parallel inductors, which is 468 millihenries. Just as we had a time constant for an RC circuit, we'll also have a time constant for an RL circuit. Notice the equation is slightly different. It's L divided by R. This is the rate at which the current changes within the inductor. Keep in mind the time constant is still going to be a unit of seconds or milliseconds, microseconds, some derivative of seconds. And with an RL circuit, a series RL circuit where you have a resistor and an inductor in series, the current value will increase with the same exponential curve that you saw with the capacitor. The current value will also decrease with the same exponential curve you saw with a discharging capacitor as well. It takes the same number of time constants and the same percentages for an inductor to reach its maximum current, the same way a capacitor will reach its maximum voltage. And same thing here, the current will dissipate with this exponential rate, the same way that a capacitor will discharge over time. So the charging and discharging curves you saw for a capacitor directly apply to the current curves for an inductor. So the only thing that we need to add to what we already understand about charging and discharging curves is that we have to know the final value of current in an inductor. With the discharging and charging curves for a capacitor, we knew the final voltage or the initial voltage, depending on whether you were charging or discharging, was always equal to the source. Well, in this case, we need to know the final value of the current, so we're going to use Ohm's law to do that. The final value of the current is your source divided by your resistance. So we're going to calculate the RL time constant for the circuit below, and then determine the current and the time at each time constant interval, measured from the instant the switch is closed. First, here's our time constant, L divided by R. We have to know the final value of the current in order to figure out how the current will increase or decrease over time. So that's Vs over R, 12 volts divided by 1.2 kiloohms. After one time constant, we're going to have 63% of the final current in that inductor. After two time constants, we'll have 86%. After three time constants, we'll have 95%. After four time constants, we'll have 98%. After five time constants, we'll have 99%. So it'll take approximately 41.65 microseconds to go from zero current to 9.9 milliamps of current in this inductor, and basically in this circuit. So just like we had the universal voltage formula for the charging and discharging curves, we also have a current formula where we can look at how the current will change when you have an RL circuit. And this formula is extremely similar to the voltage formula. The I on the left-hand side is an instantaneous value of current, the value at a very specific point in time. We have the final value of current, the initial value of current, our constant E. We have negative R times T over L, or you can think about that as the time constant multiplied by the amount of seconds that are passing by. That's your lowercase t. So this formula is something we can use if I want to know what the instantaneous value of the current is going to be some amount of time after an inductor has begun to increase in current. So we're going to determine the inductor current 30 microseconds after the switch is closed in this example. We're going to start by figuring out how much is the maximum or final value of current that is possible in this circuit. That's Vs over R, 5.45 milliamps. And then we're going to take our equation and plug in what we know. We know IF. We know the initial value of current is 0. And we can figure out R by looking at the diagram, L, looking at the diagram, and T was 30 microseconds. That's given. So we're going to plug in chug and get 2.63 milliamps. So it takes after 30 microseconds, you'll have 2.63 milliamps of current flowing in your circuit. So just like we had capacitive reactance, we also have inductive reactance. Inductive reactance is also considered the opposition to an AC signal by an inductor. So the same way that resistors have a resistance to current flow, capacitors have capacitive reactance, inductors have inductive reactance. Here's your equation for inductive reactance. So now we have X sub L instead of X sub C. So make sure that you pay attention to units always. XL versus XC. So XL is your inductive reactance for an inductor, and that's 2 pi FL. That's how we're going to calculate that. So a quick example. If you have a 33 millihenry inductor with a frequency of 550 kilohertz, plug and chug into that equation, and you'll get an inductive reactance value of 114 kiloohms. And again, the unit here is ohms. So now we have a way to take a capacitor and an inductor, put them on the same playing field as a resistor, so that we can combine all of those elements into one impedance and use that to study how an AC signal will affect a circuit. That's where we're going with this. So reactance is directly proportional to inductance. So just like with capacitive reactance, you can combine inductive reactance the same way. Inductive reactances in series will be added together. Inductive reactances in parallel will be combined the same way we combine parallel resistors. So, quick example. We're going to find the total inductive reactance for each of the circuits below. To start, find the inductive reactance for each individual inductor. For the inductors in series, we're going to add those reactance values together. For the inductors in parallel, we're going to combine them the same way we would combine parallel resistors. Ohm's law will apply to an inductive circuit the same way it will apply to a capacitive circuit. So you can find the total current in a circuit by taking the source voltage and dividing by inductive reactance. Remember you must have all your units in the same form, RMS, peak, etc. So if we're going to determine the RMS current in the circuit below, we're going to start by finding the inductive reactance. The frequency is given as 10 kilohertz. L is 100 millihenries. We're going to plug that into our equation for inductive reactance, and you'll get 6.28 kiloohms. From here, you can plug that into Ohm's law to figure out the RMS current in the circuit. Remember, the value you get out is RMS because the voltage given was RMS. All units have to be the same. When we talk about power in an inductor, ideally inductors also do not dissipate any true power. In the real world, though, a coil of wire is always going to have a very small amount of resistance we call winding resistance. That winding resistance will generate a very small amount of true power in a real-world scenario. Reactive power is also something we measure for an inductor, and it's basically the same formula we use for capacitors. We're going to take our RMS values of voltage and current and use those to calculate reactive power. We also can use the inductive reactance when we calculate reactive power, and that unit, again, is VAR. So when we study capacitors and inductors in an AC circuit, we are going to be using that inductive reactance or capacitive reactance, if you have capacitors, in order to calculate your reactive power. So let's say that you have a 10 volt RMS signal with a frequency of 1 kilohertz applied to a 10 millihenry coil, that's an inductor, with a negligible winding resistance. That means ignore the winding resistance. We're going to determine the reactive power. In order to do that, we have to know the total inductive reactance. So you're going to do 2 pi times the frequency, 1 kilohertz, times the inductance, 10 millihenries. And then you can find the total current in the circuit by taking your RMS voltage divided by your inductive reactance. And then you can calculate power using that RMS current. No, this is not the only formula you could have used. You could have used any of the formulas for reactive power. This is just the one I happen to have chosen for this problem. All of those formulas will provide the same final answer, which is 1.59 VAR. All right, so that's the end of this video. Today we laid the foundation with some more tools that we're going to start using when we analyze RC circuits. That's the next lecture. So in the next lecture, we're going to be using the idea of capacitive reactance and the idea of phasors and the idea of going from rectangular to polar and polar to rectangular in order to analyze an RC circuit with an AC source. So during the next few days or before you watch the next lecture, my recommendation is make sure you can calculate capacitive reactance. Make sure you can combine capacitive reactance in series or in parallel. Make sure you can convert from rectangular coordinates to polar coordinates and back. Make sure that you understand how phasors are supposed to be drawn and what they represent. All of that is going to come together next week for our first lecture where we actually start analyzing RC circuits. And with that, that's the end of this video.